This video is on the boundary of a set. First, let's just recall a couple definitions that are related. So first, if A is a subset of X where XD is a metric space, then a point X in X is a limit point of the set A if every open set containing X contains some element A in A other than the point X itself. So we have a set A contained in X. Little x may or may not be in A, but it's the case that every open set U, for any open set U we choose, there's some element A of A other than the point X. It might also be the case that, our X is inside of A, but even if that's true, there must be some point A other than the point X that's inside of A. We also had the definition of a closure of a set A. That's the union of A with its limit points. It's denoted A with a line above it. The limit points of A are denoted A prime, so A closure is A union A prime. We could also think of A closure as the set of elements X in X, such that every open set U containing X must contain an element of A. So if X is actually an element of A, then it's immediately true that any open set U containing X contains an element of A because X is an element of A. Or if X is outside of A, and that means that X must be a limit point of A if X is in A closure, in which case any open set containing X would contain a point of A other than X itself. So this is another way that we could describe the closure of A. So here's our new definition now. Let's let A be a subset of a metric space XD. A point X in X is a boundary point of A if X is in A closure and X is in the closure of A complement. So this is the same thing as A complement closure. So in other words, X is in A union its limit points, and X is in A complement union the limit points of A complement. It's got to be in both of those places. So kind of visually, we think of the boundary as being like points like this. Depending on the exact metric space, that might not be exactly how it really looks, but kind of conceptually we can think of the boundary. And so especially thinking of this way of conceiving of the closure above, we can similarly think about the boundary in terms of open sets. So the boundary of A is equal to the set of points X in X, such that every open set U containing X contains both a point in the set A and a point, let's say Y, that is not in the set A. And so it might be the case that X is actually an element of A or X is not an element of A, but the boundary of A is the set of all points such that any open set U contains both a point in A and a point in A complement. And it's denoted BDY of A, boundary of A. So let's look at a couple of examples. So let's first start with the real numbers and the usual metric. So in this set and this metric space, what is the boundary of the set A, where A is the half open interval from A to B with A less than B? And then second, what is the boundary of the set C equals just the 2 points 4 and 9? And then finally, in the real numbers with the discrete metric, what is the boundary of that same set? So pause, try this out on some paper, and we'll talk about it together. All right, so what is the boundary of the set AB, the half open interval from A to B, in the real numbers with the usual metric? So let's think of that alternative definition of X is in the boundary of a set A if for any open set U containing X, U contains a point of A and of a complement. So that's one alternative definition, as we saw above, for the boundary of A. So let's see. If we think about, some point out here, some point x less than A, that's not going to be in the boundary of A, right? So let's say that epsilon is the distance between x and A in this case, and that means that, for x less than A, we could think about the ball centered at x of, radius epsilon over 2, for example, and that open ball would be an open set containing x that did not intersect with A. So that would be false. X would not be an element of the boundary of A. What about x equals A? So what if we look at the point A itself? Then yes, any open set, if U is an open set and U contains A, then one property of an open set is that since A is an element of that open set U, that means there is some epsilon greater than 0 such that the ball centered at A with radius epsilon is contained inside of U. So, in terms of a metric space, we could really think about this just in terms of open balls as well. So then we see that, for example, the point A plus epsilon over 2 is an element of A, and the point A minus epsilon over 2 is an element of A complement. So that tells us that A is in the boundary of A. Now let's look at, we see that B would similarly be in the boundary of A for the same reason. B is in the boundary of A. We could use the exact same logic. Points larger than B, x greater than B, would not be in the boundary of A. Again, by the same logic as what we saw over here. So that would not be in boundary of A. And lastly, what if we have some point in between x and B, A and B? So say A is less than x, which is less than B. Then if that's the case, if we have some point x here, there's definitely going to be some ball of some radius that is completely inside of the set A. In other words, does not contain any points of A complement. So let's let epsilon be the minimum of the distances between A and X and the distance between A and B. Then it's the case that the ball centered at X of radius epsilon is completely contained inside the set A, and so this contains no points of A complement, and therefore X would not be in the boundary of A in this case. So this tells us that the boundary of the set, this half-open interval from A to B, would be just the endpoints A and B, which I think intuitively makes some sense. What about the set C containing the elements 4 and 9? So then if we take any open set U containing the point 4, then that would also contain some ball centered at 4 of radius epsilon contained in any set U. And if we take that ball centered at 4 of radius epsilon, we see that 4 is, of course, an element of it. 4 is an element of this ball centered at 4 of radius epsilon. And let's say that 4 plus epsilon over 2 is an element of this ball centered at 4 of radius epsilon. This is an element, 4 is an element of the set C, and 4 plus epsilon over 2 is an element of C complement. And so that tells us that yes, 4 is in the boundary of C. Similarly, 9 will be in the boundary of C with the same logic. What if we take any point that is not equal to 4 or 9? We could do a similar argument and say, if we have some point x, if x is not equal to 4 and not equal to 9, we could let epsilon be the minimum of these two distances, the minimum between x and 4 and between x and 9. And in that case then, the ball centered at x of radius epsilon will contain no points of the set C. Contains no points of C. To be in the boundary of a set, any open set containing that point must contain both points of the set itself and of the complement. So that tells us that x is not in the boundary of C. And so what we see is that the boundary of the set 4, 9 is the set 4, 9. Finally, let's look at the real numbers in the discrete metric for that same set. So again, we've got our set with 4 and 9, and what is the boundary of this set? So let's look at, first of all, open sets in the discrete metric. So in the discrete metric, on the real numbers, again, we know that the distance between 2 points is 0 if the points are equal and 1 if the points are not equal. So for example, the ball centered at 4 with radius 1/2 is an open set, and that open set contains only the point 4. So the ball centered at 4 of radius 1/2 is only the point 4. That's because the only point of distance less than 1/2 from 4 in the discrete metric is the point 4 itself. And so this is an open set, contains no points of C complement. So if this is still our set C, it contains no points outside of that set, and therefore 4 is not on the boundary of the set C. Similarly, 9 won't be on the boundary of the set C either. And if we take any point x anywhere on this set, then the set containing just x will be an open set as well, and that open set will not contain any points of C. So this open set containing the point x, which is not equal to 4 or 9, will contain no points of C. So if x is not an element of the set 4, 9, the set C, then again, this ball centered at x of radius 1/2 is going to be equal to just the point x. That's an open set, contains no points of C, and therefore that no point x is in the boundary of the set. So this tells us that the boundary of our set 4, 9 in the discrete metric is the empty set. This section ends by just stating that the following expressions are equivalent. 1, x is in the boundary of A. 2, x is in A closure minus the interior of A. 3, every open set containing x contains a point of A and a point of A complement. 4, the distance between x and the set A is equal to the distance between x and A complement, which must be equal to 0. And 5, x is an element of A closure and x minus A closure. So we've already talked about these two statements being equivalent earlier in this video, and we've used that fact throughout the video. I think the fact that 1 and 5 are equivalent, that's just by definition of the boundary. The boundary of A is the set of points x that are in A closure, and x is in x minus A closure. That's the definition of the boundary of x. So immediately that's the set A closure intersected with x minus A closure, or this is the same thing as A complement closure. So the fact that 1 and 5 are equivalent is immediate. showing that 1 and 2 are equivalent is pretty quick. It's sort of just left as kind of an exercise of the book, but this is pretty immediate as well. And the fact that 4 is equivalent to 1, this sort of hinted to when we think about this like distance and epsilon balls. So say for contradiction that the distance between, say, x and a equals epsilon, which is greater than 0, then the ball centered at x of radius, say, epsilon over 2, contains no point of A. So x would then not be in the boundary of A. And similarly, same deal if the distance between x and A complement was greater than 0. So understanding why this is true is pretty immediate as well. So these are all equivalent definitions or equivalent expressions to being in the boundary of a set A.